Hello. Hi, everyone. Um, Welcome to this video lecture on mathematical induction, where we do a quick refresher on the topic of principle of mathematical induction. I'm Arvindan Vijayaraghavan. I'm an assistant professor in the Department of Computer Science at Northwestern University. My main interests, research interests, are in theoretical computer science and in formally reasoning about algorithms, improving and designing improving guarantees for algorithms. Okay, great. So in this video lecture, we will see what mathematical induction is. Okay, so what this technique of mathematical induction is, and then we will see why is mathematical induction true. So we'll actually prove the principle of mathematical induction. And then we will see variants of induction, which might come in handy in different scenarios. So we'll in particular see this concept of strong induction, which is a stronger form of mathematical induction. And finally, we'll see some examples where it is the choice of the induction hypothesis will play a big role. Okay. And in illustrating these different concepts, we'll try to use at least one example each. Good. So mathematical induction is a technique that's used to show propositions. In fact, they are used to show propositions about natural numbers. Just so that we are all on the same page, what is a proposition? A proposition is just a statement. The statement could be true or it could be false. And our goal is to establish whether it's true or not. Okay, so some examples are a particular number, let's say 98459 is a prime number. Okay, this could either be a true statement or a false statement, and only one of them is true. Okay, it's either true or false. Similarly, Jack lives in Evanston. Jack is a particular person. Jack lives in Evanston. This could be true or false. So these statements are propositions. Okay. Good. And what are predicates? A predicate is a proposition which has a particular parameter. So often we'll denote this parameter by x, or in this lecture we'll use parameters k or n. And what is a predicate? It's just a proposition which has this parameter x, and which is a sort of a variable. Okay. So for instance, a predicate p of x could be the number 2 times x is an even number. Okay, and you can think of this predicate as being defined over all natural numbers. So for each different value of x among the natural numbers, you get one statement, one proposition, which you can see whether it's true or not. Okay. Similarly, another predicate over natural numbers could just be p of x is just a proposition that x is prime. X is a prime number. Okay, so in particular, p of 98459 is really the statement. So this statement just corresponds to the statement p of 98459, where p is defined here. Now, these propositions could also be on other kinds of parameters or variables, like you could have a predicate that is defined over people, and p of x could just be the statement that x lives in Evanston. Again, now, I mean, this predicate applied to the parameter x being Jack gives you the proposition that was an example listed above. Okay. Now, mathematical induction is a technique for proving predicates on natural numbers. So, so it's a technique by which you can establish that certain predicates on natural numbers are true. Okay. So, and in this lecture, we'll be using the convention that natural numbers start with 0, and they'll set 0, 1, the infinite set 0, 1, 2, 3, and so on. Okay. Note that there are other books and courses that might use the convention that the natural numbers start with 1. So you get 1, 2, 3, 4, and so on. Okay, but there isn't a very strong difference between the two. Almost all of what we'll see in this class will hold for both. Okay, it's just a question of whether you start with 0 or you start with 1. Good. So induction is a way by which you prove that a certain predicate, okay, a given predicate on natural numbers is true for all natural numbers. Okay, so here you're given a predicate P, okay, with the parameter K, and K is natural numbers. And it's just a technique for proving that this predicate is true, is a true predicate for all natural numbers. Okay, it's a mathematical technique to do this. Okay, and it turns out to be extremely powerful in establishing various statements, okay, proving various theorems in this form. And there are two steps to any induction proof, okay, any proof by mathematical induction. The first thing is what is known as the base case. Okay. So here you establish that the predicate is true for the first natural number. And what is the first natural number here? And here it's just 0. But generally, this is problem dependent. If you want to establish this predicate for all natural numbers starting from 3, then the base case would be just establishing that the predicate is true for k is equal to 3. Okay. In general, depends on the statement. Good. And the second step is to do the following. So you will prove that for all k, suppose you assume that P of k is true. Okay, so you fix a k and you assume that P of k is true. Then you'll try to derive that P of k plus 1 is true. Okay, so you want to show that P of k implies P of k plus 1. Now, how do you do it? You assume that P of k is true, and then you try to derive that P of k plus 1 is true. If you're able to do both these steps, then by the principle of mathematical induction, this predicate is true for all natural numbers. Okay, so a nice analogy that I like to tell students is, imagine a contraption of a stack of dominoes, okay, that's arranged so that all of them fall. Now, how do we set up these dominoes? Well, they're set up so that when the kth domino falls, it hits the k plus 1th domino, so that the k plus 1th domino also falls when the kth domino falls. Okay, so you set it up in this way. So that's analogous to the second step that you're doing here, which is to say that P of k implies P of k plus 1. But once you set up the dominoes like this, it's not like the dominoes will fall by themselves. You have to strike the first domino and make it fall. And that's analogous to the base case, where you're establishing that P of 0 is true. Okay, so really you can think of this predicate as being propositions, one for each natural number, and you're really stacking them like dominoes. And you're doing it in such a way that if P of k is true, then you prove that if P of k is true, then P of k plus 1 is true. And then you start with the first natural number and show that that's true. Okay, and then they'll keep following. So then that will imply that P of 1 is true. Then P of 1 is true implies that P of 2 is true, and so on and so forth until it's true for all natural numbers. So that's intuitively what mathematical induction is doing, the principle of mathematical induction is doing. Okay. Now, here it's extremely important that you establish this base case. Okay, and while a lot of the effort will go into proving that assuming P of k is true, you get P of k plus 1, you can derive P of k plus 1. The base case is often quite easy, but it is extremely important to establish it. And any proof without the base case is an incomplete proof. Okay, and this is very important because often you can prove fantastic incorrect statements by just doing the second step without doing the first step. And the pitfall in that proof will be just the fact that you did not bother establishing the base case. Okay, and that's why you'll see why the statement is wrong. Okay, good. Now let's see some examples. Okay, good. So the first example is to just show the simple statement. This is just a sum of the terms in a geometric series. Okay, we want to show that if you, for any real number r and any natural number n, we want to show that 1 plus r square up to r raised to the power of n is equal to this expression r raised to the power of n plus 1 minus 1 divided by r minus 1. Now note that this number 1 is really just you can also write this as r power 0. So really you're adding up r power 0 plus r power 1 plus r power 2 and so on. Okay, good. Now we want to prove the statement. Okay, the first step in using the principle of mathematical induction is to identify the statement that you're trying to prove as a statement about natural numbers. Okay, so really the first step is to identify this predicate. So you want to reformulate whatever you're trying to do as a statement about natural numbers. Okay, so and well, sometimes this is, in many cases it's quite easy to do this, but sometimes it can be quite challenging. Okay, but one hint is to look for with what natural numbers are present in the statement. So for instance, there are two numbers here. There's an n and an r. Well, r is reals. We want to show this for all reals, and n is a natural number. So really we want to think about it as a statement over natural numbers. So the hint here is to think about this, is to use a predicate where the parameter is actually n. Okay, so we'll try to do this by induction, and the predicate p of k will just be the statement that 1 plus r square up to r raised to the power of k is r raised to the power of k plus 1 minus 1 divided by r minus 1. Okay, so this is the predicate that we are going to establish. Okay, if we establish this predicate is true for all k, that is for all natural numbers, then we establish the theorem. Okay, and this is actually an extremely important step. The first step in any induction proof is actually to establish this predicate. Okay, so is to identify the predicate and write it down. Okay, so it may seem like, sometimes the predicate might be obvious, but in any case, it's good to identify the predicate and write it down explicitly. Good. So the first step here is to establish the base case. Okay, so what is the base case here? Well, we want to show this for all natural numbers. So let's start with the natural number 0. Okay, so let's look at p of 0. So p of 0 is a statement that r power 0. Okay, so you go up to r raised to the power of k. So when k is 0, you just stop at the first term, which is r power 0. We want to show that r power 0 is equal to r raised to the power of 0 plus 1 minus 1 divided by r minus 1. Okay, now this is true since r raised to the power of 0 plus 1 minus 1 divided by r minus 1 is just r minus 1 divided by r minus 1, which is equal to 1. Okay, so and the left hand side, this is the right hand side. Okay, and the left hand side is also is r raised to the power of 0, which is 1. Okay, so by the way, maybe in the statement you want to assume that r is not equal to 1, just so that the expression on the right makes sense. Good. So now we have established the base case because we have shown that p of 0 is true, because in that case, the left hand side and the right hand side we have established are equal. They're both equal to 1. Good. The next step is to take the induction hypothesis. So the induction hypothesis is to assume that p of k is true. Okay, so k is any natural number, and we are going to assume that p of k is true. Okay, so what does this mean? That means that we are going to assume that the statement 1 plus 2r plus r square up to r raised to the power of k is equal to r raised to the power of k plus 1 minus 1 divided by r minus 1. Okay, so assume this is true. For now, you can think of this like an axiom. So this is just a true fact. And from this, we want to derive that P of k plus 1 is also true. So what does it mean? We want to show that 1 plus r squared up to r raised to the power of k plus 1 is equal to now r raised to the power of k plus 2 minus 1 divided by r minus 1. Okay, so let's see why that's true. So the left hand side is 1 plus r squared and so on up to r raised to the power of k plus r raised to the power of k plus 1. Okay, but if you look at the first k terms in the series, okay, since P of k is true, we know that the first k terms in the series already adds up to this expression on the right, which is r raised to the power of k plus 1 minus 1 divided by r minus 1. And then you have an extra term, which is r raised to the power of k plus 1. Okay, so now we can just try to simplify this expression, and this is taking this common denominator of r minus 1, we get r raised to the power of k plus 1 minus 1 plus r raised to the power of k plus 1 times r minus 1. Okay, and if you expand this out, you get an r raised to the power of k plus 2 here minus an r. Okay, so let me actually write this out. This is equal to r raised to the power of k plus 1 minus 1 plus r raised to the power of k plus 2 minus r raised to the power of k plus 1 divided by r minus 1. And these two terms cancel, and so you just get the right hand side. Okay, so hence P of k plus 1 is true because we have now shown that this is exactly the right hand side. So now we have done both steps. We have established that the base case is true, and we have shown that P of k implies P of k plus 1. So now by induction, P of n is true for all n. All natural numbers. Okay, and this completes our proof. So this is our first proof using mathematical induction. The first step, or in some sense the 0th step, is to identify a predicate, okay, over natural numbers. So that if you show that the predicate is true for all natural numbers, we establish the theorem that we want to show. Okay. Now, once we have identified the predicate, you show that the predicate is true for the base case, which is maybe like the first natural number, or the first natural number that you want to show your statement for. And that's establishing the base case. Then you assume that P of k is true, and then you try to derive that P of k plus 1 is true. If you're able to do that, then this, by the principle of mathematical induction, establishes that P of n is true for all natural numbers n. Now, I mean, at this point, it seems like the principle of mathematical induction, and there are many, many examples of this kind that you can do. It seems like principle of mathematical induction is mainly used for showing statements about numbers. Okay, it might sound like this, but in fact, mathematical induction can be used to show some pretty amazing facts. I mean, here is a simple example. It's kind of a toy example again, but really this statement is just about chessboards. Okay, there are some numbers floating around, but really it's a statement about chessboards. Okay, so let's try to understand what the statement is going to say. Well, suppose we are given a board of size 2 to the k by 2 to the k for some k. Okay, so for instance, you can think of k as being 3. Okay, so if k is 3, it's an 8 by 8 chessboard, which is the usual kind of a chessboard. When k is 4, you can think of a 16 by 16 chessboard, which is a bigger chessboard. And let's say that exactly one of those boxes is missing or shaded out. Okay. So now what is your goal? Your goal you're given these 4 different kinds of tiles. Okay, these L-shaped tiles. You can think about these as the moves that are made by a particular piece, like a horse. Okay, and the question is, can you tile the entire board using just these L-shaped or rotated L-shaped tiles? Okay, so each of these patterns corresponds to 3 different squares, okay, which are contiguous in this L-shaped formation, or this, these rotated L-shaped formations. This is just an example. Okay, so for example, if you look at this figure where k is equal to 2, you have a 4x4 board, because this is a 2 raised to the power of 2, which is a board with 4 rows and 4 columns. Okay, and one of those tiles is already shaded out. Okay, and now we'll try to see how we can just fill up this whole board with just these patterns. Okay, tile this whole board with patterns. Here's a simple way to do it. Use this piece. Okay, let me use a slightly different colored pen. So we can use this piece and tile it here. Okay, so you can use this pattern and tile the top right corner. And now similarly, you can use this piece and tile the top left corner, and you can use this piece to tile the bottom left corner, and then the bottom right corner similarly. Now you've tiled most of them except for these three in the middle, okay, and which you can actually tile using again one of the pieces, which is this again. Okay, so this shows that you can. This is a simple way to tile a 4x4 board with this particular piece missing. But now what we are asked to show is that you can actually tile any 4x4 board, where even if this piece is not, even if it's not this particular piece that's missing, but maybe the top left corner that's missing, or the top right corner that's missing, or any piece there missing, a single piece they're missing, you can actually tile it. Okay, and you're actually asked to show this not only for boards with k is equal to 2, but any 2 to the k by 2 to the k board. Okay, good. Now, I mean, this is the kind of problem that you'll actually see in a bunch of these puzzles. Okay, and when you see it in the form of puzzle, induction is not necessarily the kind of technique that you think about, because it doesn't really look like a statement about natural numbers. Except you can actually frame this as a predicate over natural numbers as well. Okay, so here's the statement we want to show. For any integer k greater than or equal to 1, this is really just any natural number k, because integers greater than 1 are all natural numbers. You want to show that any board, there is a grid of boxes of size 2 to the k by 2 to the k with one box missing, can be tiled using these rotated L patterns. Now this, you can actually, the first step when you're trying to prove this by induction is to identify this with the statement over natural numbers. Okay, so identify the predicate. And what's the predicate here? Well, the predicate is just going to be the statement that is, so the parameter is going to be k, and it's just going to, p of k is just going to be the statement that any board of size 2 to the k by 2 to the k with one box missing can be tiled. Now, we're going to prove this by induction. So there are 2 steps. The first is the base case. Now, here, you could, in the previous example, we started out with the base case of k is equal to 0. Now here, we actually start with the base case of k is equal to 1. And the reason we do this is because, let me use a different pen. The reason we start with k is equal to 1 is because we want to prove the statement for all k greater than or equal to 1. So the first natural number that we want to prove the statement for is k is equal to 1. So we start with the base case of k is equal to 1. Okay. And so what does it mean? Here, For k is equal to 1, we are looking at all 2 by 2 grids, okay, and with one box missing. Now, for k is equal to 1, for 2 by 2 grids with one box missing, you can actually just enumerate all of them. And in fact, these are the 4 different options that you have. Okay, so it's a 2 by 2 grid with one of the 4 boxes missing. And it's easy to see that each of these can be tiled using these L-shaped patterns. And in fact, just one of these L-shaped patterns will fill up the rest. Okay, so hence the base case is true. Good. So now let's go to the next part of the statement. Let us assume that this statement is true for k. So, and let's derive that p of k plus 1 is true. So we're going to show that p of k implies p of k plus 1. Okay, so this is what we would like to establish. Let me so what we know is that this is true for all boards of size 2 to the k by 2 to the k with one tile missing. And this is what we assume by the induction hypothesis. And we want to prove that it's true for all boards of size 2 to the k plus 1 by 2 to the k plus 1. Remember that 2 to the k plus 1 is 2 times 2 to the k. Okay, so we want to use the fact that p of k is true and then derive p of k plus 1. And so really in many of these induction proofs, one of the main steps, a common step, is to use this information that you're given, that p of k is true, as effectively as possible. So you want to prove something about k plus 1, you try to see how you can use the fact that you know that it's true for for k, as effectively as possible. And here, if you think about it a little bit, the best way, one way to do this is to actually split up this whole board, okay, which is of size 2 to the k plus 1 by 2 to the k plus 1, into 4 boards, okay, of size 2 to the k by 2 to the k each. So there were 2 to the k plus 1 rows and 2 to the k plus 1 columns. Now each of these are going to be 2 to the k. Okay. Now, well, if you look at the bottom right board, it is clear that this is actually of the form of a board of size 2 to the k by 2 to the k with one block missing. Okay. Now, this one block that's missing has to fall in one of the 4 quadrants. So let's say it's in the bottom right quadrant. Now, the bottom right quadrant exactly satisfies the properties that is needed to apply p of k. So p of k will tell you that this bottom right corner by itself can be tiled with these L-shaped patterns. But what about the other 3 quadrants? Here's a simple thing you can do. Okay, you just use one of your tiles to fill up these 3 squares. Okay, so now all 4 of these quadrants are of the form of the 2 to the k by 2 to the k board with one block filled in. Okay, so each of these 4 quadrants. So each of the 4 pieces is a board of size 2 to the k by 2 to the k with a box filled in. By induction hypothesis, we know that p of k is true. So each of those 4 pieces of boards can be tiled using these L-shaped patterns. And together with this middle tile, we have tiled the whole board. Okay, so hence we can tile the entire board. So this implies that p of k plus 1 is true. So we established the base case in the previous slide. Now we established that p of k implies p of k plus 1. So by induction, the theorem is true. So p of k is true for all k. So we looked at two examples where we actually saw how we could use induction to prove yeah, various mathematical facts. And again, the steps were you want to first identify the statement that you're trying to prove as a statement over natural numbers. Okay. Then the first step is to establish the base case, and then you try to show that P of k implies P of k plus 1, and then by the principle of mathematical induction, this is true for all natural numbers. Good. Now, in the next video, we will see why induction is true, and then we will see some stronger variants of induction as well.